This video explores the topic of gesture recognition based on time-of-flight sensors within the framework of the European project titled Personalized Education in Measurement Science and Technology, Empowered by Machine Learning. Today we'll explore how time-of-flight sensors, together with embedded systems and software tools, can accurately detect hand gestures in real time. You'll learn the principles behind gesture recognition and see a practical example of how such systems are implemented. Modern electronic systems interact continuously with people. Unlike traditional interfaces like keyboards, buttons, or touchscreens, which require physical contact and visual attention, gesture recognition allows machines to respond to natural human behavior, creating a new, intuitive way to interact with technology. We'll go step by step, from basic concepts to sensor technology, hardware integration, software architecture, and finally a working gesture recognition system, so you can understand how these systems operate in real-world applications. Let's start by understanding what gesture recognition is. Gesture recognition is a technology that allows systems to detect, interpret, and classify human movements, such as hand gestures, arm motions, body movements, or facial expressions. These movements can be static, like a hand pose, or dynamic, like waving. Gestures act as a natural communication channel between humans and machines, enabling interaction without keyboards, buttons, or touchscreens. Systems use sensors to capture motion and spatial data, signal processing to denoise and structure the data, and algorithms, often involving machine learning, to interpret gestures. This means the system must understand where the movement occurs and how it evolves, which is why depth sensing and other advanced sensors are critical. Why is gesture recognition important? First, it enables touchless interaction, which is crucial in medical settings, industrial environments, and public spaces where hygiene and safety are essential. Second, gestures are intuitive because humans naturally communicate with movement. This reduces the need to learn complex interfaces and improves user experience. Third, gesture recognition enhances accessibility, allowing people with physical disabilities to interact with systems that would otherwise be difficult to use. Finally, gesture recognition plays a major role in gaming, robotics, augmented and virtual reality, smart homes, and automotive interfaces, providing fast, immersive, and natural interaction. It also improves efficiency and automation in workplaces, allowing machines to respond directly to human intent. In short, gesture recognition transforms how we interact with technology, making it more natural, inclusive, safe, and efficient, while enabling a wide range of applications that require spatial awareness and dynamic interaction. Gesture recognition is a key aspect of human-machine interaction, which focuses on making technology respond to human intent naturally and efficiently. Unlike traditional systems, where humans had to adapt to machines, modern human-machine interaction strives for machines that adapt to humans. Gestures are a particularly powerful form of communication because they are nonverbal, fast, expressive, and largely independent of language. Gesture recognition systems enable machines to interpret these movements, translating them into digital signals that computers can understand and respond to. For this translation to feel natural, it must be accurate, fast, reliable, and robust. When done correctly, gesture recognition reduces both cognitive and physical effort, creating interactions that feel intuitive and effortless, bridging the gap between human behavior and digital technology. A time-of-flight sensor measures distance by emitting infrared light and measuring the time it takes for that light to travel to an object and return to the sensor. Since the speed of light is constant, the distance can be calculated very precisely using a simple formula: the speed of light multiplied by the measured time, divided by 2. This measurement is repeated thousands of times per second. As a result, the sensor generates a depth map of the scene, which is a three-dimensional representation where each pixel contains distance information. Unlike conventional cameras, which capture only color or brightness, time-of-flight sensors directly capture depth. Although the underlying principle is simple, measuring such extremely small time intervals is technically challenging. Thanks to modern semiconductor technology, these measurements can now be performed with high precision, making time-of-flight sensors practical, compact, and affordable. The measurement process follows a clear sequence. The sensor emits an infrared pulse, the light reflects off objects in the environment, such as a user's hand, The reflected light returns to the sensor, and internal electronics compute the distance based on the travel time. The result is a real-time 3D view of the scene. Depth information is especially important for gesture recognition. Gestures take place in three-dimensional space. Hands move toward and away from the sensor, and the system must distinguish the hand from the background. Depth sensing solves these challenges by adding a third dimension to perception, independent of color or lighting conditions. Time-of-flight sensors are therefore particularly well-suited for gesture recognition. They provide high-depth accuracy, support real-time processing, work reliably in low-light or no-light conditions due to active infrared illumination, and are robust to background clutter. In addition, their compact size and low power consumption make them ideal for use in mobile devices, robots, augmented reality and virtual reality systems, and other embedded platforms. The sensor used in this project is the VL5-3L5CX, a multi-zone time-of-flight distance sensor developed by ST Microelectronics. Unlike single-point distance sensors, this specific sensor measures distances across multiple zones simultaneously, allowing it to capture spatial information about the observed scene. The sensor can operate in 4x4 mode, providing 16 measurement zones, or in 8x8 mode, providing 64 measurement zones. Each zone delivers an independent distance measurement, effectively dividing the field of view into a grid. This multi-zone output enables the system to understand the spatial distribution of objects, which is essential for recognizing hand shapes and tracking motion during gesture interaction. The sensor features a wide field of view, allowing it to observe a large area of space. This is particularly important for gesture recognition, since user movements are not always perfectly centered or aligned. Combined with multi-zone sensing, the wide field of view produces a coarse depth image that is sufficient for reliable gesture recognition while keeping computational complexity low. The sensor supports distance measurements up to 4 meters and is capable of detecting multiple targets within each zone. It also offers high frame rates, reaching up to 60 Hz in certain configurations, which enables smooth and responsive tracking of fast hand movements. Despite its advanced capabilities, this sensor comes in a very small package and has low power consumption, making it well-suited for embedded systems. Additional built-in features, such as optical crosstalk reduction and robust operation under ambient light, help maintain reliable performance in real-world conditions. Overall, the VL5-3L5CX sensor provides an efficient balance between spatial awareness, performance, and computational simplicity, making it an ideal choice for embedded gesture recognition applications. The VL5-3L5CX time-of-flight sensor supports a wide range of applications thanks to its ability to provide accurate, real-time depth sensing. It is used in gesture recognition and gesture-based user interfaces, robotics navigation and obstacle detection, as well as object detection. The sensor also plays an important role in smart lighting systems and smart buildings by enabling user detection and adaptive control. Additional applications include liquid level measurement, laser-assisted camera autofocus, video projector keystone correction, and augmented and virtual reality systems. Although these applications appear diverse, they all rely on the same sensing principle, reliable depth information that enhances system intelligence. This slide illustrates the internal architecture of the sensor and explains why it delivers reliable performance in challenging conditions. The sensor integrates a single photon avalanche diode array, infrared optical filters, and diffractive optical elements into a single system. The single photon avalanche diode array is made of extremely sensitive detectors capable of registering individual photons, which enables very precise timing and accurate distance measurements even when the reflected signal is weak. The optical filters and diffractive elements ensure that only the relevant infrared light reaches the detectors, effectively suppressing unwanted signals. Together, this integrated design reduces noise, improves measurement accuracy, and makes the sensor robust across different lighting conditions and materials, which is key to its high performance. This slide presents the pin configuration and application schematic of the VL5-3L5CX sensor, highlighting how it is integrated into a real hardware system. This sensor includes power supply pins, I2C communication pins, control and reset pins, and interrupt outputs, all of which must be correctly connected to the host microcontroller. Reliable operation depends on proper voltage levels and correctly sized pull-up resistors on the I2C lines, as incorrect wiring or missing pull-ups can lead to unstable communication and unreliable behavior. This schematic also illustrates how different voltage combinations enable flexible integration with various platforms, showing the transition from theoretical concepts to practical hardware implementation. Overall, this slide emphasizes that successful sensor integration requires careful hardware design and brings together multiple aspects of embedded engineering, including electronics, power management, digital communication, and signal integrity. From the software perspective, the sensor is controlled through an API provided by the ST Microelectronics company. The sensor itself is purely hardware, while all intelligence and control come from software. The API abstracts the sensor's internal complexity and enables developers to focus on application logic rather than low-level details. Through this interface, the software can initialize the device, control the ranging process, select operating modes, and acquire measurement data. The sensor supports multiple power states, ranging from low-power idle modes to full-range operation. This flexibility allows the system to balance performance and energy consumption according to application needs. Efficient power management is therefore a key aspect of system design, especially in battery-powered, mobile, and IoT devices, where minimizing power consumption is critical for long-term operation. The VL53L5CX time-of-flight sensor communicates using the I2C protocol, which is a widely used serial communication bus in embedded systems. I2C is a simple but powerful communication protocol, allowing multiple devices to share the same bus while using only two wires, SDA for data transfer and SCL for the clock signal. However, correct timing, addressing, and acknowledgements are essential for reliable operation. Because of its simplicity and broad adoption in sensor-based designs, understanding I2C is essential knowledge for embedded engineers. During a write operation, the controller communicates with the sensor using a defined sequence. It first sends a start condition, followed by the device address, the target register address, and the data bytes. Each step is acknowledged to ensure reliable and error-free transmission. Through this process, configuration data is written to the sensor, allowing the controller to set operating modes, enable specific features, and adjust internal parameters according to the application requirements. During read operations, the sensor transmits measurement results back to the controller. To make this process efficient, an auto-increment addressing feature is used, which allows consecutive data registers to be read automatically without repeatedly specifying new addresses. This enables fast transfer of large data blocks, such as multi-zone distance arrays, and is especially important for quickly reading multiple zones in applications like real-time gesture recognition. This sensor can operate in two configurations, a 4x4 mode with 16 zones, or an 8x8 mode with 64 zones. Each zone represents a specific spatial region in the sensor's field of view and provides distance measurements. Accurately mapping these zones to their real-world locations is essential, as this spatial information forms the foundation for gesture recognition, motion tracking, and gesture segmentation. Because of the optical design of the sensor, the image of the zones is flipped. This means that software must properly map the sensor zones to their real-world positions. Correct mapping is essential to ensure gestures are interpreted accurately. This demonstrates the importance of understanding both the hardware optics and the software handling together. This slide explains the factors that define range measurement accuracy. Key elements include target reflectance, distance, ambient light, temperature, calibration, and noise. All of these can influence measurement results. Understanding their effects is essential for engineers to design reliable and robust systems. To implement the system, we will use two interconnected boards, the VL53L5CX SATL breakout board, which houses the VL53L5CX time-of-flight sensor, and the STM32F429 Discovery microcontroller platform, along with the corresponding software. ST Microelectronics provides a complete software ecosystem for their microcontrollers, which reduces development time and lowers the barrier to entry for complex sensor systems. STM32Cube is ST's comprehensive and free software platform that simplifies STM32 development by offering a suite of PC tools and portable embedded software libraries. This ecosystem accelerates the design process from concept to product while minimizing effort and time. For this project, we will utilize Xcube TOF1, a software expansion package for STM32 microcontrollers specifically designed for time-of-flight sensors. It provides drivers, middleware, and sample applications, enabling features such as single-sensor ranging, multi-sensor data acquisition, and gesture recognition. Built on the STM32Cube ecosystem, Xcube TOF1 ensures portability and simplifies development by providing ready-to-use solutions for sensor calibration, ranging, and multi-sensor management. The VL53L5CX Saddle Breakout Board is a compact development board featuring VL53L5CX time-of-flight sensor designed for easy integration into projects by providing an 8x8 multi-zone depth map with up to 4 meters range, enabling 2D gesture sensing, obstacle avoidance, and room mapping through its I2C interface, and featuring a unique design where the sensor's mini PCB can be broken off for smaller applications. The STM32F429 Discovery Kit is a discovery board from ST Microelectronics, a feature-rich development kit built around the high-performance STM32F429 ZIT6 microcontroller with an ARM Cortex-M4 core designed for beginners and experienced users to create graphics-intensive applications. The key characteristics of the board are summarized on the slide. Understanding the hardware layout is crucial in embedded development, as it directly impacts signal quality, system reliability, and overall performance. A well-designed layout is especially important for high-speed digital communication, ensuring that signals remain clean and the system operates efficiently. This slide shows the top layout of the hardware. In this slide, we can see the hardware's bottom layout. Understanding and using debugging tools like StreetLink is crucial in embedded development. These tools provide programming and debugging capabilities, enable real-time data monitoring, and allow observation of internal system states to verify correct behavior. This slide explains how to connect the VL53L5CX Satel breakout board directly to the STM32F429 Discovery Kit board for development and testing. These boards provide a complete platform for rapid prototyping, experimentation, and learning, allowing engineers and students to focus on key concepts without worrying about low-level hardware details. They are ideal for research, education, and hands-on testing of new ideas. This slide presents some key features of the Xcube TOF1 software expansion. The software stack is organized into 3 layers: the HAL layer, the BSP layer, and the application layer. This layered architecture is standard in professional embedded system design and enhances portability, scalability, maintainability, and reliability. This slide shows folder structure of the Xcube TOF1 software package. The simple ranging example demonstrates how to acquire raw distance data from a sensor, send it to a microcontroller, and display it on a serial terminal. This complete data flow forms the foundation for more advanced processing, including gesture recognition algorithms. The next slides will guide you through a step-by-step explanation of how this simple ranging example is implemented. Step 1. Open STM32CubeMX and select Access to Board Selector. Step 2. Select the STM32F429 DISC1 board. Step 3. Start project. For board project options, STM32F429 DISC1. Select No Mode. This action triggers a window shown in the right image. Step 4. Select Connectivity, then select I2C3. Next, select Enable I2C, and finally select Standard Mode. Step 5. Select Connectivity, then select USART1. Next, select Asynchronous. Select the pins PA9 and PA10 for TX and RX. Set baud rate of 115,200 baud. Step 6. Select middleware and software packs, then select Xcube-Cube-OF1, then select VL5 3L5CX. Next, select Application VL5 3L5CX _ simple ranging, and finally, OK. Step 7. Configure the GPIOs for the application and configure the I2C, USART1, and BSP. Step 8. Configure the GPIOs for the application system view, shown left, and pinout view, shown right. Step 9. Select Project Manager. Step 10. Name the project, select Toolchain, and then select Generate Code. Step 11. Select Open Project on the pop-up window when code generation is complete. Select the directory as Workspace and press Launch. Step 12. Main window appearance in Cube IDE tool and Configuration Settings window for program run. Step 13. Open the Terra term and configure it with the settings shown in the slide. Step 14. Apply the following settings. Terra term serial port setup 115,200 baud and Terra term terminal setup receive set auto for new line. Final step 15. The following data is displayed in the terminal window. Sensor initialization process, launching the distance measurement application, execution control characters for the application, display of measurement results in cell format according to the selected sensor operating mode, 4x4 or 8x8 multi-zone ranging sensor. This slide illustrates the results of a time-of-flight-based gesture recognition system. By analyzing multi-zone depth data, the system successfully recognizes simple hand gestures, such as like and dislike, demonstrating the practical effectiveness of this approach. When the application is running, distance measurements are displayed in real time on a serial terminal, allowing direct visualization of hand positions and movements. This visualization plays a key role in debugging and validation, as observing the raw depth data makes it easier to understand how different gestures influence the measurements and to verify that the system behaves as expected. To conclude, time-of-flight sensors provide a robust and effective approach to real-time gesture recognition by using precise ranging data to track hand movements over time. Gesture recognition algorithms analyze these distance patterns to reliably identify simple gestures, demonstrating the accuracy and practicality of time-of-flight sensing. When integrated with STM32 microcontrollers and supported by modern software tools, time-of-flight sensors become part of a complete and efficient development ecosystem. This combination enables contactless and natural human-machine interaction while supporting scalable hardware integration, structured software architecture, and real-world embedded implementations. Looking toward the future, the integration of time-of-flight technology with machine learning and sensor fusion will enable more advanced, adaptive, and robust gesture recognition. As a result, this technology is expected to play an important role in next-generation smart systems, robotics, healthcare, and human-centered computing. Thank you for your attention. This video was produced through the collaboration of SS Cyril and Methodius University of Skopje, the University of Niš and Politecnico di Milano, within the framework of the European project Personalized Education in Measurement Science and Technology Empowered by Machine Learning. More information about the project can be found on the project website and LinkedIn page.